Hello. Hi. It's like echo. Are you all awake or what? It's like one person. Give me some noise or something so I know you're like not. Fantastic. That's what we like to see. Hi, I'm Tejas. That's pronounced like advantageous for those of you who aren't used to exotic Indian names. And whether or not we are advantageous, we'll find out at the end of the talk. You can come tell me, or you can tell me on Twitter. But I work at a company called Zeta. It's like data, but with an X. And really what we do is we work a lot in the database space, which is why today I am here to talk to you about doing data as a front-end developer. Doing data as a front-end developer. And I think this is important, and here's why. It's important to me because, like, have any of you, show me your hands, or maybe not, have any of you felt like imposter syndrome when you're a front-end developer? Yeah, show me. When you're a front-end developer and you hear a back-end conversation about a database, right? It's like NoSQL, MySQL, your SQL, our SQL. Which one? So I genuinely believe, from self-experience, that imposter syndrome is a thing. And early in my career, as a front-end developer, I tried to play in the database field a bit and was told, hey, why don't you go back to moving your pixels? That's the industry, by the way. And so today I work at a database company doing DevRel, and I know a bit about databases, and I figure, you know what, let's eliminate some of your imposter syndrome here. That's the goal. Is that good? Like the goal here is education and information, okay, about databases. So to do that, let's unpack this word data a little bit, because it's a loaded term. It can mean many things. As a front-end developer, you have data in the browser, so you have mechanisms like session storage that gives you data for the current session that goes away when you close a tab, or local storage that is like scoped to your domain, a key value store, where if you're not smart about your keys, any like JavaScript running on your client side can read your key password, local storage.getItemPassword. So you want to be a bit careful with that. There's indexed DB that helps you build powerful offline first apps with tremendous amounts of blob storage and things. But if you're a front-end developer, I'm assuming for the purposes of this talk, you've played with these things. They're part of the web APIs. The limitation of this is when you want to share data across multiple devices and sessions. If you want to build a cohesive experience on an iPhone or a laptop or whatever. And so that you'd probably use data in the cloud for. Data in the cloud. Now, to understand and unpack data in the cloud, which is kind of what I want to spend the bulk of our time on, we need to go to a far and mysterious land. A deep forest, maybe guarded by a dragon or something. I call it the backend. And like, especially if you're like laser focused on front end, it can be scary and mysterious. But if I ask you, if I'm like, hey, can you explain to me in your perspective what is the backend, right? I've asked a lot of people in preparing this talk, what is the backend to you? Can you like illustrate it for me in a diagram or something? And I was surprised because I got a lot of this, which I'm hoping my phone doesn't slide down. There's like an angle here. Okay, so I want to do this with a diagram. I want to show you what I hear often, and that's this. If we exit out of here, go to my diagram tool, shout out Excalidraw. Love some good Excalidraw. What's the backend? So if we draw a little diagram, we have a UI. It's very much not the backend. We have another, like an API that talks to a data store or a database of some sort, right? And what your UI is going to do is talk to your API, which is probably going to talk to your database. Bada bing, bada boom. That's the backend. And I hear this a lot. But from what I've seen, it's a lot of complexity. And this is what I want to kind of make a point about. The UI world has a lot of complexity because you're working in a forward environment, right? Different network conditions, different browsers, the backend, we control a lot of the variables, but there's still a lot of complexity. And that's because backend includes DevOps. So like, instead of your app directly talking to your API, that's probably not the case. You're probably going to have something called a subnet, which is kind of what it sounds like. A sub-network, a range of IP addresses that is not publicly exposed to the internet. You're going to then have like some type of application load balancer, or ALB, which lives in a public subnet. And I'm using Amazon language because it's the cloud I'm most familiar with, but whatever you enjoy. So your app's probably going to talk to something like this that has access to your private subnets that's going to do this. But the other interesting thing is all of this happens in what is called on AWS anyway, I did not want to save that, is called an availability zone, or an AZ. And there's multiple availability zones in a region across the world geographically, like US West, US East, which has had some issues lately. And if you speak AWS, all of this happens, and this is, by the way, still a simplification. All of this happens inside a virtual private cloud. So there's your backend, and there's your simplified backend. It's very complex, okay? For the purpose of doing data as a front-end developer and understanding and eliminating imposter syndrome, I kind of want to focus, I want to zero in on this DB side, okay? Let's talk about specifically the database. Now, if you've been around conversations about databases, there's almost always a question that shows up. There's almost always a decision point that shows up. And this is SQL or NoSQL. It's almost Shakespearean, to SQL or to NoSQL. And it's a hard question because NoSQL doesn't even mean the absence of SQL. It could, but you can query some NoSQL systems with SQL or SQL. So some now say it's not only SQL, so NO, it's complicated. In fact, I think this is not as close to as accurate as the other terminology, which I think is relational versus non-relational. This is the way we reason about data, and I think it's more true to the systems. Do we choose a relational data store or a non-relational one, and why? If you have imposter syndrome about the space, let's talk about that. Relational systems are sometimes called SQL databases. We'll use SQL and NoSQL just for this talk. I just want you to know that I mean relational and non-relational. To understand this question, we need to go through like a time journey, a chronological journey, okay? In the early days, relational databases were the premier art for data storage and for data access. Why? That's what I want to explore. And they still are, by the way. They're still in high demand. But why were they so popular in the beginning? Well, number one, you got a structured language, a really awesome way to interact with these things, to query them. This is called SQL, or structured query language, and it's the most declarative, beautiful, in my opinion, I love this. It's like, if you want to get data, select columns from table where conditions limit 5. And you run it, and it's there, you know? It's so declarative, it could like eat React for breakfast. You know, like everyone's like, oh, JSX, it's so declarative. I'm like, have you seen SQL? Right? And so it's this comfortable way to query your data. This is what made it really popular. Number two, normalization. It's generally a good practice to reduce data redundancy through the relational model. And I'd like to show you a little snippet of normalization. I think it's better to show than to tell. So I'm going to go to my database here called Cascadia. And it's a database with branches. It's a branchable data. Anyway, so we have a redundant branch. And in this, we have a students table with some columns. It kind of looks like a spreadsheet. That's because it is. And these are students like in a school system. Okay? And you've got some students in grade 10, 11, 10, 11 with ages. But what's not ideal about this is the data is redundant. Grade 10 repeats, grade 11 repeats, and I can't store like more metadata about the respective grade. A normalized approach, and this is a very contrived example, by the way, a normalized approach would suggest maybe factor out your classes into different tables. So now we have two tables, students and grades, and if the internet cooperates, there we go. So now this is no longer just an integer, but it's a reference to the grades table, which can have, you didn't see the object, which can have a grade and a teacher associated, like as metadata. And through normalization, we take full advantage of the relational model, like this table connects to that one at this column, right? So normalization was really valuable to reason about your data and connect things together. Another huge selling point and a good positive argument for relational databases is ACID transactions, or ACID guarantees. To understand ACID transactions, we need to talk about what a transaction is. Transaction, for the purpose of this talk, is a collection of operations, like create, update, delete, okay? What makes them ACID? ACID is a backronym. That's an acronym that's actually a word. What does it stand for? It stands for 4 guarantees that you get with transactions in a typical relational database. The first one is called atomicity. That basically, in essence, means a single unit of work. Transactions are treated as a single atom. So if you do create, update, delete, they either all happen or none of them happen. The guarantee of atomicity gives you the comfort that if something happens between update and delete, you'll not end up in this like Frankenstein state where something was created and updated but then not deleted. Your database will either be in the state you expect after, or if something fails, it will roll back and it'll be in the state you expect before. You can imagine why this is valuable. It makes your data predictable. Number 2, consistency. This is like TypeScript, but at the database level. If you have a column of type number, it is guaranteed to always be a number. If you try to insert a string, your database will insult you. Number 3, transactions happen in isolation. So you could run like 1 million transactions in parallel, but they don't interfere with each other such that after they all finish running, it looks as if they ran sequentially. You know what I'm saying? Like they're very separate. And if you have a bunch of operations that depend on each other, like create this, then update the thing that was created, you would batch them into a transaction. So transactions are nice and separate. Number 4, the D in ACID is durability. This means that if your database server exits, or if you close your machine or something happens, your data doesn't go away. Some in-memory databases don't have durability. So durability is awesome because if something breaks or something goes off, your data is just going to be saved somewhere. These guarantees made relational databases so popular, they basically owned the web in the early days. But eventually, as you go years and years and years, and you accumulate what? You accumulate tons of data, okay? And that's when we started to notice some limitations. This is very hard to scale, because the best way you can scale a non-relational single server, a relational single server database, is by scaling vertically. That is adding resources, memory, disk space, and so on. It's like making your building large, right? Scaling vertically. Problem is there's a ceiling. You eventually build a supercomputer that contains a lot of resources. It's expensive to maintain, and you're like, and it's also, in a way, a single point of failure. It's just very hard. And then you can maybe do like a primary replica situation. That is hard. Why? Because of your relationships, because it's relational and so on. So we started to notice some limitations. Enter NoSQL, or non-relational, built as a response to the limitations of relational databases that were considered superior. Non-relational databases are built like for scale. They're literally built with one job, that is to scale massively. And the way they can do that is they're essentially key value stores. It's like a JavaScript object. You have a key, you have a value. And just like with a JavaScript object, the key is unique, and the value doesn't necessarily have to be a scalar type. It doesn't necessarily, I'm speaking faster than my mouth. It's this 25-minute thing, man. Anyway, the values don't have to be scalar types. They could be objects that are deeply nested. They could be whatever. This comes with a caveat, right? It's unstructured. You don't get the consistency guarantee. So you could have key A with value string, key B with value array, key C with value object. It becomes scary if you don't manage it. But because of the unique keys and values, these databases are heavily partitionable. In fact, the largest, I think, maybe I'm wrong, maybe something changed. The largest non-relational database in the world, I think, belongs to Apple. It's a single database that spans over 75,000 servers. It's massive, right? And this is because of the non-relational model. Now, this presents a problem. How do you know when you want to read something from 75,000 plus servers, or you want to insert something, like which server? It's a problem. By design, most of these systems, what they do is they take the unique ID of your record, pass it through some type of hashing function, depending on the database, and come out with a number that falls in a range. So you could have server 1 be range 0 to 100, server 2, 100 to 200, server 3, 300 to 400. The hash is computed into one of these, and then it knows which machine. It's a high-level abstraction, but that's kind of how it works. And that range of numbers is called the key space. You usually have very large key spaces across multiple servers. Now, ACID was a set of guarantees for relational databases. Of course, they had to do this. Tech people are creative, man. So non-relational databases give you a set of really characteristics that kind of sum up into something called base. Base stands for, it is basically available. That means it prioritizes availability over other things. So you'll always, given a request, you'll always get a response, but this response may be stale because of something called replication lag. If you have a bunch of servers, you write to server A, it may not spread to the others, and then you read something old. Second tenet is the state is considered soft for the same reason, and all of these are kind of the same thing. People just wanted base, I think. It's eventually consistent, because again, if you send a write and the data hasn't replicated across your cluster, if someone does a read before it replicates, you get stale data. We're seeing in the industry a new term, a relatively new term, because like people want the awesome stuff from relational databases, from SQL. They want the scale from NoSQL. And so why not just bring the two together and create new SQL? And there's a Wikipedia page about this. It's when people try to get the best of both worlds. They try to get the awesome ACID transactions from relational, but also the just easy horizontal scale of non-relational. And this is being called NewSQL. And what I've noticed is there's a bunch of offerings of NewSQL systems in the industry, but most of them are managed because it is complexity that you would rather like pay someone $25 to manage instead of like pay a bunch of salaries for. And there's probably the most common player in this is AWS Aurora. It's like the widest used probably. There's a product called FaunaDB, some of you may have heard of this, which gives you a non-relational database, but with ACID transactions. They implement something called the Calvin protocol to do that. It's a fascinating read. And of course, where I work, that's kind of what we're trying to do, is give you the convenience of SQL with just arbitrary scale. Now, though, I can hear you. I can read your minds. Okay, maybe I can. Honestly, I can't. I'm just being funny, or trying to. You know, whatever. He just told me I have 10 minutes, so I can fool around a bit. I don't need to move as fast. Anyway, I hear you asking, which one? Which one should I use? Should I use MySQL or NoSQL or what? And I'm gonna answer you with the most stereotypical, classic engineering answer there is. You know it? Can you say it for me? You read my mind. You see, I like it. It depends. What does it depend on? So if I'm building like a banking app, right, and I need to know my bank balance right now, I need that immediate consistency, right? I would probably go with something relational. Can you imagine? I make a payment and it doesn't deduct, and I'm like, it was free. So I need strong consistency. I'd probably use a relational store. However, if I'm building like a social media site, like Reddit, and I want to show you the number of upvotes, I don't really care if it's 2005 upvotes or 2007 upvotes, whatever. Also, replication lag is usually order of milliseconds, so it really doesn't matter. It's not as important as money. And so I'd use something non-relational. But can I maybe, hypothetically, ask you a question for a question? So you asked which one. You didn't, my slide did, but still. You asked which one. I ask, why not both? This is like my go-to question. Every time I'm in an engineering decision, should we use Kafka or something? I'm like, what? There's probably a reason to use both. Let's take the example of this banking app. I need to know my balance right freaking now. I don't really need to know my balance last month quickly or with some. It's going to stay consistent anyway because like I can't spend money last month today, right? So eventual consistency doesn't even matter. So both would look like for this month, I use a relational data store. And then when the month lapses, I store it in a non-relational store, and you can pull it up whenever you want. It can't be stale because it's not going to update. So we use both this way. In fact, I would submit to you that data infrastructure matters a lot more than the choice of database. What we have with the bank thing is a relational and a non-relational setup that really forms data infrastructure. And if we revisit that diagram in the beginning, shout out again, Excalibur, what we have here is database. This is not actually true. Like if we adjust this, we have our relational, right, or rel. We have our NR, non-relational, that we orchestrate. As we accumulate data volume, we're going to probably have some type of in-memory cache because databases usually write to disk and it's slower than random access memory. And we're probably, as we accumulate a ton of data, pardon my messy diagram, we need a search engine, this forms data infrastructure, right? And this is the stuff that is worth thinking about probably more than which one database do I use and why. And so I'd really recommend moving in that direction. Now, that was a lot. Hopefully, we've understood relational, why it was popular, non-relational, why it's popular. Now maybe we can even participate in some discussions where we previously felt imposter syndrome. Let's land this plane with some takeaways. Takeaway number one, tribalism bad. Okay, like I'm part of tech Twitter. How many of you are on tech Twitter? Right, I expect you to follow and tweet me. I'm just joking. But, like, tech Twitter is just, sometimes it drives me up the wall. Why? Because, like, it's always a fight. You know, you have people in this, like, React bubble tweeting, like, put JSX in the browser, you cowards. I'm like, but why? Why am I a coward? JavaScript in the browser is fine. It's just your bubble, you know? And then there's the Svelte bubble and this bubble and that. Tribalism, it's a problem. Look, I want to remind us here, CascadiaJS 2020, we have like immense privilege of choice in the open source web ecosystem world. I can build something with Vue and React. Imagine that. I have actually, just to make a point. We have the privilege of choice. And I'd encourage, as a takeaway, data infrastructure could be relational, non-relational. We don't need to segregate into camps. That's going backwards. I really think cooperating and blending things is the way to go. Number two, integrity good. By integrity, I mean, like, sure, we could go philosophical and talk about, like, I mean what I say, interpersonal integrity, whatever. But I mean, like, that too, yes. But data integrity is really important. So knowing your data is going to be there, it's going to be safe, it's going to be redundant, which is usually a negative term. In this case, it's good. Redundant data means you have copies and backups. Thinking along these lines as you participate in these conversations where you're no longer an imposter is good to think about. And lastly, data over databases is key. And I'll tell you why, because data comes with, I heard Uncle Ben once say, with great data comes great responsibility. And so we need to think more about the data we're using. Is it likely to lead to machine learning bias? Is it people's personally identifiable data? Do I need to store this much and this urgently? That part of it, but also the part of infrastructure. Do I need a non-relational cache? Do I need a search engine? Data is far more complex than your choice of database, and I think that's an important takeaway here. And with that, hey, I'm hoping I eliminated some of your imposter syndrome. I'm hoping you were able to have more conversations that we want to, and maybe even as we start our own companies, like pick the right database for the choice and form powerful data infrastructure. With that, I want to thank you so much, CascadiaJS, for having me.